In this math talk, we're going to address how to work with triangles that are non-right angle triangles. In other words, what we call oblique triangles that do not contain a right angle. And we have to recognize that we can't use SOHCAHTOA to deal with triangles that are non-right angled. Or what I should clarify there is to say that if we do use SOHCAHTOA by doing some constructions on that triangle, the problem becomes a little more complicated, and there is something much more efficient, or two rules that we have that are much more efficient. And the first one we're going to look at is what is known as the sine law. So we'll start with a triangle ABC, and this triangle is drawn so that no angle is 90 degrees in this. Now, at that point, we need a system for naming the sides of the triangles. So what we do is this. We look at a vertex A, and we look at the side across from vertex A, and we refer to that as little a. So across from angle C, we would mark that side little c. Now, to develop the sine law, I'm going to make one more construction, and that will be an altitude drawn down from vertex B down to the side AC. What I'm going to do is try and find some trig ratios involving A, H, C, angles A and angle C. And the first one I'm going to write down is this one. It's going to be that sine of A is H over C. Now, if I isolate H in that equation, I get C sine A is H. Similarly, I will take the expression sine C, or the trig ratio sine C, and write it as H over A. That too can be rearranged to be A sine C equals H. Now we have two expressions both equaling H. C sine A equals H, A sine C equals H. Recognizing that both the left sides equal H, we can equate them and say that C sine A equals A sine C. And what we see here is a really, really nice symmetry between the left side and the right side. I'm going to make a slight modification to that symmetry by dividing both sides by A times C. And in the process of doing that, on the left-hand side, my C's will divide out, and on the right-hand side, my A's will divide out. And I'm left with a really clean expression that is sine A divided by A equals sine C divided by C. And this is going to work in any triangle. Now, you may say to yourself, well, A and C, the angles that I chose, were kind of arbitrary. Well, you would be right. I could have developed this relationship involving angle A and angle B, or angle B and angle C. So logically, if we call the third side little b, the relationship would look like this, that sine A over A is equivalent to sine B over B is equivalent to sine C over C. And if you prefer, you can rewrite that equation as A over sine A equals B over sine B equals C over sine C. You really only need to remember one version. However, having said that, I tend to use the first version if I'm searching for an angle, and the second version if I'm searching for a side. Now it's important to recognize where you can make use of these. Your decision to use the sine law will depend on the information that is provided. And so the first type of triangle that we might consider, or we should consider for using the sine law with, is one where we are provided with two sides and a non-contained angle. In other words, that angle isn't pinched between the two sides. That angle is opposite one of the two sides that we know. That would be one example where we would use the sine law. The second would be a situation where we have a single side and two angles. In this case, I've drawn them so that the side is contained or pinched between those two angles. But just as easily, we could have two angles and a side. So in other words, the side isn't contained. In any of those three situations, we would use the sine law. But what's really important to recognize is every situation involves either two sides and an angle or two angles and a side. And then we'll talk about what would happen if we weren't in one of these three situations in a further video. Let's try some examples. In this question, we are being asked to solve triangle ABC for all missing sides and angles. In this, we're provided that Angle B is 82 degrees. Little b, the side across from the 82 degrees, is 15, and little a is 8. Well, I recognize that I have two sides and a non-contained angle, a perfect sine law situation. So I will start by writing my complete sine law, and then take a look at the information that I have provided in my question and see what exactly I could solve for. Well, I have angle B and little b. I have little a, but not angle A. So I'm thinking I should probably use sine A over A equals sine B over B. Filling in the values, I get sine A over 8 equals sine 82 over 15, and now I isolate for sine A. So I multiply both sides by 8. At that point, in order to get A, I just take the inverse sign of the expression on the right. That gives me A equaling approximately 31.9 degrees. Often we round these to the nearest degree, but for now I'm just carrying an extra decimal place. Now that I know angle A, it's very, very quick to get angle C. I just use the angle sum triangle theorem, so I take my 180 degrees for my entire triangle, and I subtract off the two angles of 82 degrees and 31.9 degrees. That leaves me with angle C equaling 66.1 degrees. Just one last step now to get the third side in our triangle, and that's to use the sine law again, and I'm going to use little c over sine c. You can see I've turned my sine ratio the other way with the sides on top because I'm after a side. So little c over sine c is little b over sine b. Filling in the values that I know, and then rearranging the equation, I get 15 sine 66.1 degrees over sine 82 degrees. And that value works out to 13.85. And so all the missing sides and all the missing angles have been found. Angle A being 31.9 degrees, angle C being 66.1 degrees, and little side C being 13.85 units. Now on to a second example. We've got triangle PQR. In this situation, I have provided two angles and a side, and that side is contained between the two angles. Now you may look at this and say, wait a second, across from the two known angles, I have two unknown sides. Across from the known side, I have an unknown angle. Well, once again, we start by recognizing that a triangle has 180 degrees in it, and so we can find that third angle really quickly. And it looks like this. Angle P would be 40 degrees. Now I use the sine law, and I'll use little p over sine p is equal to little q over sine q. Filling in the values that I know, 6.5 over sine 40 degrees equals q over sine 78 degrees. Isolating for q, I just have to multiply both sides by sine 78 degrees, and q works out to a value of approximately 9.89. So that's one angle, one side found. I now just have to get my third side. Once again, employing the sine law, r over sine r equals p over sine p. Filling in the values that I know, I get r over sine 62 is 6.5 over sine 40. Isolating for r, I get r equals 6.5 sine 62 over sine 40. Finally, r is 8.92, and now we have all missing sides and angles, so the triangle is solved. Now let's examine an application. In fact, one that we looked at earlier. And the question reads, from opposite ends of a 300-meter wide bridge, the angles of depression to a point A on the water below the bridge are 22 degrees and 61 degrees. Calculate the height of the bridge. Previously, when we drew our diagram, we had split up our bridge length into 300 minus x and x. We now no longer need to do that. The sine law allows us to deal with the fact that we don't have a right triangle. We will still be able to find h. And this is how the solution would go. I'd look at angle A, which has the unknown angle value right now, and easily grab that by taking 180 degrees, subtract the 22 plus the 61 degrees. So I'm basically taking away the two angles of depression to find out that angle A is 97 degrees. At that point, I use the sine law, which says little b over sine b is little a over sine a. b over sine 22 degrees is 300 over sine 97 degrees. And so that leads to b equaling 300 sine 22 degrees over sine 97 degrees. Now at that point, I'm not even going to grab the value of b. I'm not going to try and find the value of b. I don't need to, remembering that all I'm asked to find in this question is h. I then look for an expression involving h, and it looks like this. H over b equals sine 61 degrees. So h must be b sine 61 degrees. Well, I have an expression for b, so I'll put that into my equation, 300 sine 22 degrees over sine 97 degrees times sine 61 degrees. Now that's quite a bit different from the expression that we had before when we broke the triangle into two right triangles. But in the end, we get the same answer, 99 meters. So essentially we've given you a new tool called the Sine Law that allows you to address triangles, solve for sides and angles in triangles when that triangle that you're dealing with is non-right angled, and that's one very powerful tool. Having said that, it's not the cure-all for all triangles. We will hit some triangles where the sine law will not get the job done for us. Fortunately, in the next video, we'll talk about the cosine law, and that will complete the set of tools that we need to solve any triangle. Thanks for watching. We'll see you in the next video.